Hello friends, in this video we are going to discuss about the converse of the Lagrange's theorem. That is not true, right? So we are going to conclude this by studying the example of A4, the group alternative group of order 4 A4. Okay? So to know about alternative group, we must know about the group Sn, the symmetric group Sn, right? So let us discuss that first. We know that the group S4 is nothing but the group of permutation of the set 1, 2, 3, 4, right? And we also know that there are n factorial elements in the group Sn. Hence, there are 24, that is 4 factorial elements in this group S4, which we are going to list. The first element is identity. This identity, then we have 1, 2, 3, 4, 5, 6, 2 cycles inside the group S4. The next we will see is nothing but the 3 cycles. In the group S4, we have 1, 2, 3, 4, 5, 6, 7, 8, 3 cycles. Okay, just note each and every element of S4 because this is necessary. The next we go for 4 cycles. There are 1, 2, 3, 4, 5, 6, 4 cycles in the group S4. In total, till now, we have 7 plus 8 plus 6. Total 21 elements we have listed. Still 3 elements are remaining. Those are product of 2 cycles. That is 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. These are the total 24 elements of the group S4. Okay. Note this thing. Now we are going to talk about transposition. What is a transposition? A permutation of the form A comma B where my A and B are not equal is called transposition. In a simple word, it is nothing but a 2 cycle. Any 2 cycle you have, you can call it as a transposition. Okay. Now one thing, how many transpositions are there in the group S4? Yes? There are only 6 transposition in the group S4. We know that the permutation of the form 1, 2, 3, 4 is not a transposition, but it is a product of 2 transposition. There are 3 product of 2 transposition in the group S4 and there are only 6 transposition in the group S4. Okay. Why this thing is more important? Why we want to discuss this transposition or a 2 cycle? Because of the next theorem that tells me that any permutation in Sn where n is greater than 1 is a product of transpositions. What this theorem trying to tell us? It is telling us if you have any permutation, for an example, I take a permutation 1, 2, 3, 4, 5, then that can be written as product of transposition as this. Let us just verify this, that this gives me the given transposition. This transposition gives me the given permutation. Okay. So 1 goes to 5, 5 goes to 2, hence 1 goes to 2. Then 2 goes to 5, 5 goes to 3, hence 2 goes to 3. Now 3 goes to 5, 5 goes to 4, hence 3 goes to 4. 4 goes to 5. And also 5 goes to 1. Hence, this is nothing but a transposition representation of a given permutation. The question arises, is this representation unique? Can you write in some other way? The answer is yes, you can write the given permutation in some other form of transposition also. Since I could write my given permutation as a product of this 6 transposition. So we know that the theorem was just telling us you can write every permutation in terms of a transposition, but there is no unique representation. But we observe over here, in the first representation, we required 6 transposition, whereas in the second representation, we required 6 transposition. So this is something which our next theorem states clearly. Let us see the next theorem. The theorem states that any permutation can be either represented as a product of even number of transpositions or the product of odd number of transpositions. That means what? That means if one permutation is represented by the product of even number of transposition, then any other representation of the permutation will have even number of transposition only. That means if I write this permutation in terms of a transposition, since once I require even number of transposition, any other representation you try to write will require even number of transposition only. Okay, and similar goes with the odd transposition also. Okay, so this theorems take it close to the group in which we are interested. Just note everything down. Now we are going to write a transposition representation of every element of the group S4. This is just for the practice purpose. If you could write the first few, you can skip the video. Okay. The first is the 3 cycle 1, 2, 3. The one way in which I prefer to write this is like this. That is 1, 3, 1, 2. What I do is I map the first element with the last, then the first element with the second last. Let us just verify for this one. I start from this side, so 1 goes to 2, and the second transposition 2 goes to 2. Hence 1 goes to 2. Now start with 2. 2 goes to 1, then 1 goes to 3. So 2 goes to 3. Now 3 goes to 3, 3 goes to 1, hence 3 goes to 1. Hence this is right? This is something which I prefer. You can go in other form also. But one thing that we note over here, I require 2 transposition. That is nothing but the even number of transposition. By the above theorem, we know that any other representation you try to write, you will require even number of transposition only. Similarly, can you write for this? I have 1, 3, 2 as a 3 cycle. You can write this is same as 1, 2, 1, 3. Okay. I hope you understood it, and you can try for the other questions also. The last 3 cycle is 1, 4, 3. Guess what should be your answer? Yes, according to our method that we are going with, we will have the transposition representation as 1, 3, 1, 4. These are nothing but all of the 3 cycles that we have inside the group S4, and we note that each of them require even number of transposition to represent it. Okay, let us move further to 4 cycles. If I give you the 4 cycle 1, 2, 3, 4, by the similar pattern, you are supposed to give the answer for this. You will map 1 to 4, then 1 to 3, then 1 to 2. Let us just see. Right? You can verify that it is right or wrong. Okay. Similarly, I try to write each of the 4 cycle in terms of transposition. We know there are how many 4 cycles? 6. So I try to write all of 6 in terms of a transposition. We note that we require odd number of 2 cycle, that is transposition, to represent any 4 cycle. Correct. Now let us talk about the identity. Can I write identity also as a product of 2 transposition? The answer is yes. Since the theorem tells us any permutation of Sn can be represented as product of transposition. So what transposition I could use over here? Can I use 1, 2, 2, 1? Yes. These are nothing but the 2 transposition you can verify. If you just make the composition, you get your identity. Also, you can write the permutation and some other representation also. One of them that I noted is 1331 2443. Note, once we required even number of transposition, any other representation you write will require even number of transposition only. Okay, let us go close to our topic. Let us now define what is known as a even permutation. I hope you can guess. A permutation that can be expressed as a product of even number of transposition is called an even permutation. Few important and interesting theorems about even permutations are: a set of all even permutations of Sn forms a subgroup of Sn that is called alternative group of degree n, and that is denoted by An. Okay, so our example is A4 that we are going to study. That is nothing but alternative group of degree 4. That is nothing but set of all even permutation in the group S4. One more important note regarding this is, there are exactly half of the element of Sn is even permutation. Therefore, if there are n factorial element in Sn, there are n factorial by 2 elements in An. Okay. So, how many elements are there in A4? We know that in S4 we have 4 factorial, that is 24. Hence in A4 we will have 12 elements. Let us just try to list those. One of the element is identity, because we just now saw it requires what? It's required even number of transposition to represent it. And also, since An is a group, it must have identity inside it. Correct? So let us just list those elements. The first 4 or 5 elements that I listed over here is identity, then 3 product of transposition that we had in S4, and one of the 3 cycle, because we know it required even number of transposition to represent it. Similarly, if I consider this 3 cycle, it also required even number of transposition. Not only this 2-3 cycle, any 3 cycle you take will require even number of transposition to represent it. Hence, these are nothing but total 12 elements of the group A4. We note that in A4 we had A3 cycle, 3 product of 2 transpositions and 1 identity element, and we get the 12 elements of A4. Okay. Now we are going to see what is the statement of Lagrange's theorem. The statement is, in a group, a finite group, a group which is finite, the order of subgroup divides the order of a group. And this is that person Lagrange who gave the statement. One interesting fact is, the statement was never given in terms of an abstract algebra, but the statement was abstracted from other mathematician branch to abstract algebra, and the statement become really famous and really important statement in the abstract algebra. What this statement tells us? The statement is telling it that if you take any finite group, then order of a subgroup divides the order of a group. Let us take an example. Example that I consider is, suppose if I have a group of order 12 and H is any subgroup of this G, then by the statement order of H divides the number 12. That is, my order of H can be either 1, 2, 3, 4, 6, or it could be 12. Correct? The thing to note is, the converse of the Lagrange's theorem is not true. But if I try to write the converse, what it could be? It could be stated as, in a finite group G, if n divides the order of a group, then there exists a subgroup of order n. Let us just see something about it. We know this is not true, but the first counter example for the converse of a Lagrange's theorem was given by the mathematician known as Ruffin in 1799. Here is the pic of a roofing. We are going to study the group A4. We know that this is a group of order 12. 6 divides the order of a group, that is 12, but there won't exist any subgroup of order 6. If I am able to prove this, I can say that the converse of the Lagrange's theorem is not true. Correct? So in our head, we have a claim that A4 is a group of order 12 which has no subgroup of order 6. Okay? Let us just come to the proof, but before that, we are going to require some properties of the cosets that are really important for us. The first is H is any subgroup of G, then H is same as AH if and only if your A is an element of H, or I could say that H is not equal to AH if and only if A is not an element of H. Okay, interesting property. Let us see the next that will be required to us. That is, the cosets are either equal or they are disjoint. If they are not equal, they must be disjoint from each other. Okay. Let us see the third property. The third property says that your coset going to partition the group. That means if you are going to collect all possible cosets, then the union of them will going to give you your group. Okay. Fourth and the important one is the cosets have equal cardinality. Means if one coset has a cardinality 6, then other coset of it will have a cardinality 6 only. Okay.